Okie dokie, let's do this. Welcome to another Meyer Sound webinar. How's the transmission? Can everybody hear me? Can everybody see me? Excellent, thank you very much for confirming. Today is going to be all about Milan AVB, so without further ado, let's look at the household notes before I start introducing today's guest lecture. Okay. So as I said, today is about AVB, Milan AVB. We've been talking about it a great many deal during prior webinars, but today we have a special guest lecturer that will take us on a very exciting journey into this very interesting technology. But before doing so, let's look at the Zoom communication platform first. For those that are joining us for the first time, you're likely to have a window in front of you, not unlike the one you see over here. If you would like to see who else is joining you on today's webinar, please click on the participant button in the bottom of your screen, which will bring up a window on the right side showing your fellow attendees. We encourage you to ask questions, and our guest lecturer has approved of doing so, but in order to have you ask the questions in an organized fashion, we very much encourage you to make use of the raise hand feature. Whenever you press raise hand, a blue hand icon pops up in the corner of my eye informing me that you're about to ask a question, at which time I will try to find a white space in our guest lecturer's narrative and interrupt him to pose the question on your behalf. Now, in order to ask the question itself, we encourage you to make use of the chat feature. If you click on the balloon icon at the bottom of this window, the right pane splits in half, bringing up a new dialog with a field at the bottom where you can enter your message. If you would like to address everyone on the call, that is to say if you would like to address the nation, then enter a message over there and please hit enter. However, should you happen to see a family member, fellow colleague or friend, then you can also address that message to that person in private. That pretty much concludes the household notes, and that means that those that are joining us through the Facebook user community, Meyer Sound user community Facebook group, we're currently simulcasting. Welcome to you as well. The Facebook group is growing at a steady pace. Currently has over 8,800 members and rising. So welcome to you as well. As always, the framework is the Precision Toolset. We've discussed many topics by now, but today is going to be all about connecting these devices together using Milan AVB. And that means that I'm very honored to introduce today's guest lecturer, none other than Richard Bugg, our digital products solution architect. Richard, thank you very much for doing this. Thank you very much for being here. How are you doing, sir?
I'm marginally cognizant today.
Excellent. Well, then in that case, I will stop sharing my screen, and by all means, please take it away.
Thanks. You know, that's the fastest way of getting an audio professional to be quiet is to turn their mic on. So what I'm going to talk about today, let's see, how come my share didn't come up? Oh, here we go. It's this button. Curious, it said sharing didn't fail to start.
Okay, try again, please. There we go.
All right.
Confirmed.
Thanks. So what I wanted to chat about today was AVB. Oh, and of course now the arrow keys aren't working. TSN and Milan, and a bit about Pro Audio. So we've discussed on these lectures all sorts of cool things and how we're using Meyer technology in a variety of ways. And what we're going to look at today is what's happening with AVB and AVB TSN and Milan, and how that all fits together in various applications in order to make your life a little bit easier. So we'll come back to these use cases towards the end. But first, let's start with the rhetorical question, Why audio over Ethernet? What is it that we gain from having audio on Ethernet? Wasn't analog fine before? What does putting audio and video on a network actually mean to me? I mean, seriously, what was wrong with analog? When I started out, well, gee, it's really only been 45 years ago. Analog was just fine then. So what has changed? Well, it turns out that we have a cost associated with maintaining high quality audio over the analog transport. There's a signal degradation that takes place the further we go. And if we want to have any kind of remote control, we've got to put in additional infrastructure. So after we've converted the audio to digital, which is outside of today's discussion, what do we gain by having our media on the network? Well, there's no quality loss. Once we're in the digital domain, that digital data that we start with at the talker end is the same digital data we get at the receiver end. We've got a considerable advantage in physical cabling. So if you think of the cost of a 288 channel analog snake versus the cost of Cat5e or Cat6 Ethernet, there's several orders of magnitude difference between what you pay per foot on that, plus termination costs and maintenance. When I was starting out, I never thought of just leaving the snake behind and going to the next venue. It's not particularly green, but it is an option that one could actually consider if you had a problem on a touring rig. Just leaving that cable buried in the ground for somebody else to dig up and recycle. We can carry our control and our monitoring on the same network as the audio. So we've got one cable infrastructure that runs. And we can do monitoring things that in the past we never would have thought was practical at all. Because if we're talking digital devices to digital devices, there's all sorts of details and interesting effects that you can, interesting information you can get back. And then we have our connectivity and routing flexibility. You know, there's this concept of the audio cloud that you may have heard mentioned before. And this means that instead of having to have contingency tie lines and some backup cables run and the rest, we're now able to use a network infrastructure and go out and query devices that are plugged into the network to get their performance, how things are going on, is it actually plugged in, is it happy, is it healthy? So it's pretty amazing the amount of data that you can pull back. It also means that if you're a system tech, you can keep record of how every device in the entire system was performing. And this might be a system tech on tour, but it might also be a building facilities manager. We've got some deployments now where people are using building monitoring software in order to not only take care of HVAC and inventory management and telecommunications throughout the venue, but they're also monitoring their sound system so that they can tell how things are behaving, how they're being used. They can schedule preventative maintenance in advance because they know just how many hours have been run on a device and how long it's gone. So it's really opening up a whole new way of looking at your infrastructure. So we've got high quality transport, we've got this remote control and monitoring that's available, and we've got a decrease in our physical plant cost. And we get all of this for running our media over the network. Now, we should stop for just a moment and think about the original intent of Ethernet. And that's quite a broad topic in and of itself. But basically, the original design of what has become known as Ethernet was to guarantee reliable delivery regardless of adverse any kind of adverse situation. So timely delivery was secondary to making sure that the message absolutely positively got through regardless of what was going on. That's great if you're sending critical text messages around, if you're sending a message to a printer, if you have time at the other end to reassemble that message. And of course, I mean plenty of computer time, so 300 or 400 nanoseconds. But what does it mean if we're trying to deliver audio and our audio doesn't arrive in order, or parts of it go missing and have to be resent? You either wind up with a very dramatic pause, which isn't very effective in the middle of a musical performance, or you wind up with all sorts of audio artifacts, little ticks and snats and rude sounds, and all of a sudden my expensive concert ticket has turned into me listening to an 8-bit greeting card digital chip playback. That's likely to lead to some objections on the part of the audience. So what is it that we require from Ethernet in order to use it in a professional audio application or professional video? You know, we move media over the network. For my convenience, I'm going to refer to it as audio, but really we're talking about audio or video and moving. Well, the first thing that we really want to have is low latency. So we want to make sure that not only does the information arrive in order, but also that it's fairly prompt to do. If we're doing a playback, if it's a movie or some kind of broadcast, you're already time delayed. I watched a film just last night that was time delayed by about 40 years since it was shot. 40-year wait between the downbeat and the audio actually getting to your ears, again, is something that's probably not going to go over well with most audience members. But in addition to low latency, we also need to make sure that that latency time is constant. We refer to this as being deterministic. So if we have a latency that's low most of the time, but occasionally stretches out a bit, this makes it very, very difficult for live performers. And it provides, you know, you wind up with a cognitive disconnect on the part of the audience. So we need to make sure that not only do we have low latency, but that that latency is constant from moment to moment. We also need to make sure that our message gets through, that we don't wind up with dropped packets or things out of order. So we need guaranteed bandwidth. So our total ask is we need to make our latency latency every bit as important as the reliability of audio over as any data over the network. Of course, there's one more thing that we actually we need, and this is a method of discovering and enumerating and connecting and controlling our devices. So we sometimes refer to this as AVDEC. So if you've heard the term AVDEC or AVDEC controller, which is a bit redundant on the last bit, this is what we're talking about, is we need some method for discovering those devices that are out there. The enumeration comes from if the manufacturer has chosen to make certain control parameters available to us, we need to be able for our controller to enumerate those controls so that they can be represented to us on our control surface. It needs to be able to manage the connection. What devices am I going to connect to? What devices am I going to connect to each other? And finally, the control. How do I start and stop the audio from flowing? So the answer to all of this came about with some IEEE standards that are commonly grouped together, and they were first known as AVB, Audio Video Bridging. And this was because the IEEE standards group that first started pulling all these bits and pieces together and getting modifications and updates to the standards to make it all work, referred to themselves as doing audio and video for bridges. However, there's more than just Pro A and Pro Video applications that benefit from having time-sensitive networking. You've got automotive, certainly, which is now starting to move data around in the vehicles, including backup cameras, and the entertainment control system, as well as parts of the vehicle navigation. And you have automation that's used in large-scale manufacturing. So it's very important that the punch press come down at the right point in time, or that that container of molten steel gets poured only when the mold is underneath. So time-sensitive networking was adapted as the term to cover all of this. So what do we get from AVB? It basically enables the things that we were just talking about. It's deterministic, it's guaranteed. We can do audio, we can do video, we can do our control messages, anything that has to get there when it's important that it arrive at the right time. And it can live on the same network with other kinds of traffic, whether it's the musical instrument digital interface version for Ethernet, whether it's open sound control or OCA. The idea behind putting things onto a standard transport is that you actually empower more things to happen. Another critical part of AVB is bandwidth reservation. So when we go to set up a media connection between two devices, we can actually go through hop by hop in the network and query everybody and make sure that there is enough bandwidth available so that packets aren't going to be discarded or go away, so that we actually are guaranteed that our packet that we send with our critical audio data will make it from our talker all the way down to the listener. And what's even cooler about this is I consider myself to be an audio professional. I'm not some kind of network geek. So the last thing I want to hear is 45 seconds until showtime. Oh, would you open a terminal window and please type the following commands, followed by something that seems like it might be English, but doesn't really make a whole lot of sense to my frontal lobe. So AVB TSN takes care of this by providing a structure where this bandwidth reservation is automatically set up by nature of using these particular standards in the way that we do. We've got traffic shaping. So if we are sharing the network with other traffic, which is the whole point of this, we need to make sure that there's a certain amount of control of who gets through the door, so that we don't have to wait 2 weeks for some packets to get through while others come through immediately. So AVB provides traffic shaping. This means that your talker device has a set of cues that manage and sort out the priorities of the traffic. And again, while you can do this with other schemes, the beauty of AVB is this is taking place automatically. You don't have to get in there with a terminal window and type up and do a bunch of configuration to make this happen. While we're moving stuff around on the network, we can also support multiple media clocks. The media clock in AVB is actually treated just like any other media stream. So whether it's audio or video, it can also be the clock that's routed around. And this means that we have the ability, when you need it, of having different media clocks that are available on that. We've got simple connectivity. So this means that once you figure out how AVB is going to be working for you, the tools that are provided are taking care of a lot of the IT department stuff automatically and under the hood. And finally, we've got real-time synchronization that's available for our transport over the network. So precise timing is all about where we're at with this time-sensitive networking. And the timing is actually built into the very devices that provide the AVB support, AVB TSN support. So that's the technology underneath. The great thing about the IEEE standards for all of these things is they all provide lots and lots of options. And when we first got started with AVB, there were quite a few choices that engineering and software developers had to make in order to decide what elements were actually going to make sense for a given device. As you might have noticed or surmised, whenever you have a large group of people and a large group of options, not everybody takes the same option. And this can lead to some challenges if you're trying to get a bunch of devices connected together. One of the things about AVB TSN is being an open standard. It's not controlled by some central product owner that dictates to every user exactly what they're going to do. So this meant that people could take a look at their application and make a good faith effort as to, oh, this makes sense that I should implement it this way. The result was challenging for end users. So for those of us who are audio professionals, all of a sudden there were all these options that we had to set correctly. And the reaction, certainly my reaction was, hey, what's the deal? I thought this was supposed to happen automatically for me. I wasn't the only one that had that thought. And as a result, in 2016, there were a group of manufacturers who had been working with AVB TSN, who were very excited about it, who had products that were doing well, but looked at the entire ecosystem, what was going on, and said, you know, we could do better for this. And this really is something that will benefit all of us, because as we benefit our users and make it easier for our users, they'll be able to do more and better things. And they'll be able to have a tool that makes it possible for them to see the same advantages that we've been seeing all along, but without the pain that we've all been experiencing. So Milan was created. And what is Milan? Well, Milan is actually a protocol, and it's built using all of those building blocks of AVB that we've been going over. So there were a group of us. The initial meeting had all the major loudspeaker manufacturers, had a couple of console manufacturers, had a microphone manufacturer on that. If you all are interested, the Avenue Alliance has some nice historical data up on the website that goes into some of the history of putting all of this together. But we basically sat down and decided we needed to come to an agreement. We needed to decide exactly which of all of the stream format options that were available to us under AVB would we decide to pick for Pro Audio. We needed to decide of all the media clocking structures that we could set up, what makes the most sense for the Pro Audio, Pro Video applications. Redundancy was something that you could implement in any number of ways under the AVB IEEE standards. And redundancy means a lot of different things to different people. So if you're going to have redundancy, what does redundancy mean, and which of the choices would you make in order to make sure that when I set up my Meyer sound redundant device and I want to connect to an Avid console that we're both talking the same language and expecting the same parameters to be passed back and forth. And then we've got network control and management. So what makes the most sense for us as audio professionals to be able to see what's going on the network, but not distract from our core values and core interests, which is high quality audio from the performer to the listener. And finally, how do you manage this and make sure that anybody that claims to be Milan is actually following all the rules, and that our customers can have confidence that when they buy a device that has a marking on it that says it's a Milan device, that it will actually work and follow all the protocols and specifications and will actually adhere to all the agreements. So this is why Milan exists. We've got some features to go over on Milan here that I'll touch base with. We decided that we would put the burden of flexibility on the receiver. So a transmitter is allowed to make a choice and just kind of stick with it. And a receiver has to be able to receive stream formats. And these are the defaults. So you're allowed to go far beyond this if you want. But for interoperability, the lowest common denominator or the common language is our stream formats have to be 1, 2, 4, 6, or 8 channel. They use the AAF format. This is AVTP audio format. For those of you who might be new to the IT world, one thing that I've discovered is that if you think audio professionals use a lot of acronyms, the IT universe has us beat. So that stands for Audio Video Transport Protocol Audio Format, or AAF for short, and that it would be a 32-bit word. The listener has to be able to receive and deal with any one of those base formats. The talker, I might have an AVB microphone, a Milan microphone, and I don't want to have to build the necessary electronics into that device to support a bunch of different formats and the rest. I want to keep it as small and compact and as simple as possible. So the burden's on the receiver to be able to take whatever the talker is sending, as long as it's within the agreed upon menu of base formats that are available. And this means that if we're running Gig E Ethernet, we can do 360 channels and and those fit in 45 frames at a 48K sampling rate. By default, we only use 25% of the available network bandwidth, which leaves tons of bandwidth available on a gigabit Ethernet link to do other traffic. It used to be called legacy traffic, but it's just non-time sensitive traffic. Can take up to 25% of the network bandwidth. But again, this is a convention. If you needed to dial that up to more, you needed to crank a lot more time sensitive traffic over that, you can make an adjustment. The controllers allow for that. Or if you have non-time sensitive network traffic, but you have lots of it that you need to move over that particular link, you can also dial it back down. And once that parameter's been set, as you set up talkers to listeners with your controllers, the network automatically knows what it can allow, what can be accommodated on that pathway. So here's another table that just shows you our format is AAF. This is a PCM based format. It's 32 bits. The channel sizes for our interoperability are 1, 2, 4, 6, or 8. Our sample rate, it's mandatory that you support 48K. 96K is optional. It's interesting. Most everybody that's doing Milan these days is doing it at 96. It's what our users have been asking for, and it's what all of us have been delivering. But again, there's that lowest common denominator to provide for interoperability. Also running at the lower sample rate, you can fit a lot more channels on a stream and on a link. So if 48K is fine for you and you need lots of channels, this is an option that's readily available. We can do a little over 200 channels at 96K, and that we're doing it with 8 channel streams. And there are some devices out there, I haven't seen anything shipping yet, but 192K has also been discussed within the group. So let's talk about some terminology here. We've got an entity, which is an AVB capable piece of hardware, sometimes called an endpoint. A stream, you'll hear us refer to stream. This is the actual flow of data, and an Ethernet cable can have streams going in both directions. That's always something that, being old school analog, I have to remind myself that it's not just one end of the wire going to the other end. It's actually data flows in both directions. And a stream would be audio data, 1 or more channels. Or it could be a clocking stream, what we refer to as CRF, clock reference format stream, that has our media clock information. We've got a talker, and a talker is that part of an entity, that part of an endpoint that can send AVB streams. Source is the origin of that stream. So talker and source are, what's the term, synonyms? We've got listener, and a listener is that part of the box that can receive AVB streams. And sometimes that's referred to as a sync. So it depends upon whether you're talking to an audio professional or if you're talking to somebody who's more of a software developer mindset. So talkers and listeners. Then you have a controller, and this is the software that runs. There's several third-party controllers that are out there. There are a bunch of boxes that have controllers built into it. Certainly the Meyer Sound Galaxy has a very nice controller built in, but it also plays nicely with third-party controllers that are out there, because that's part of creating this common ecosystem that makes it possible for all of our customers to go out and do cool things and take advantage of AVB TSN. So this is kind of how you see things put together. And I think I should have redone this slide, but I was trying to pare this talk down from the 400 slides I had originally pulled down to something a little more manageable for the 20 minutes we're spending together today. So how do we put this together? To quote Soundheim, we put it together bit by bit. See, musical theater and a digital pun there. This goes so much better when I get live feedback from the audience. This whole remote lecture thing is a challenge. So we've got time synchronization, we've got discovery and control. Reliability is very important. We've got the transport, and that's what we're using AVB TSN for. And then we've got interoperability, which is what is all summed up by Milan. So let's dive into these and see how each one of these applies. So the question with time sync is, how do we make sure that in this infrastructure that was originally designed to absolutely positively deliver a bit of data reliably, how do we move that over so that not only is it reliable, but it also arrives on time and low latency? So what is it that, that we need to do? Well, first let's think about this for a moment. Our brain is sensitive to slight timing offsets. It's very annoying when things don't fit the rhythm that we were expecting. It triggers a reaction, and that often is to the detriment of the aesthetic experience. If we take a mono signal and we time shift it between two outputs, we have a difference that, you know, you could refer to it as a time offset or a phase shift on that. If we take as little as 0.1 milliseconds, we get this nice comb filter in our acoustically coupled source that's sitting right there at 5 kilohertz. Now, if this is happening due to reflections off of walls and the rest, our brain interprets that and we form this mental image of the acoustic space that we're in. If we're listening to music coming out of a loudspeaker and this starts happening in the middle of the performance, we have a cognitive disconnect, and all of a sudden we may not be conscious of exactly what's going wrong, but it no longer sounds quite the way it's supposed to. If we're doing stereo listening on headphones and we start moving as little as 1/10 of a millisecond on just one side, we perceive a change that's going on. And of course, if we're doing video and audio and we get outside of leading by 15 milliseconds or lagging by 15 milliseconds, all of a sudden we've got lip sync problems. And it's interesting watching what happens to an audience when this sort of thing is going on. Not everybody catches on to exactly what's going on, but there's, again, there's this cognitive disconnect. So, all right, we've got two computers talking together. We've got electricity that moves really rapidly through those wires. What's so hard about doing sync data on a network? Well, our network throughput times can vary depending upon the amount of traffic that's going through. And we're talking pre-Milan, pre-AVB here. So these are the challenges that were with us at the start as everyone started working out, you know, how can we actually pull this off? So the reasons for that: increased network traffic, if we've got more switch hops, if we've got some traffic that's happening further away than others, then we wind up with path differences, and sometimes it's Chip and Dale trying to go through the door at the same time once you get to a particular point in the network. And if our endpoints have no common clock reference, if we don't have that BNC cable connecting everything together with the master word clock, then when is that data actually supposed to be pushed out the jack of the device itself? So if we look at the propagation through a network between some devices from a microphone to a loudspeaker, this is, of course, perhaps slightly exaggerated here, but you can see there's a delay as we go across that. So how do we deal with network delay? What we do is each media packet includes not only the audio data, but also a timestamp. And this timestamp is set in the future. It's the time when the device is actually going to push that out of the box. So now we are sending all of our little bits of audio data around to all of our Milan AVB devices, and they're taking a look at the timestamp that's on it, and as long as they all have the same time, they all push that packet out at the same instance. And this doesn't matter how many hops away they are, as long as you're within the limits of our hop count for networks. We'll get into that in a moment. But it does mean that all of our endpoints, all of our listeners have to have a common time clock. So I think there are some of us who need a nap. Let's do a little bit of math here. You've seen, I'm sure, the specification of 2 milliseconds for AVB. This is the default setting. This is what everybody agreed would be the default. You can dial this back much shorter. And the 2 milliseconds comes from wanting to have a large number of switch hops on a network and make sure that the end devices, our listeners, have enough buffer inside that they can be able to accommodate this kind of worst case setup. So if we take a look at a presentation time offset of 2 milliseconds, each audio packet has 125 microseconds of audio data in each one of the packets. If we've got some legacy traffic on there that's trying to get out the port first, we might be held off by as much as 12 microseconds on a gigabit Ethernet. So that would be if we had a really large packet. The maximum size for normal Ethernet packets is about 1,500 bytes. So if our talker is getting ready to send a Milan packet and a legacy packet at almost the same time, but it pushes out the legacy packet first, we're going to have this 12 microsecond delay. So if we do 12 switches between our listener and talker, that's 14 hops. So 14 hops times our 125 microsecond plus 12 microseconds, assuming microsecond per switch, a very reasonable assumption there, since they're usually a fraction of that. We get to 1.918 milliseconds. So in computer terms, we've got tons of time left over before we hit our 2 millisecond offset. So this is where that 2 millisecond comes from, and how that comes about. So here is our network again without our time sync. So you can see, I'm not sure why I'm using an analog clock display there. It is a digital world these days, but you know, watching hands spin around is entertaining to my cat. So as we move around, if we don't have clock sync, we have this problem. So how do we actually get network data synced up? How do we establish this common time reference? for everything on the packet? Well, there's a nice solution there from the IEEE. And that came about with the 1588 standard. And 1588 defines common time references. And you may have heard this referred to as PTP. That's the Precision Time Protocol. And the great thing about 1588 is there are quite a few ways that you can actually implement Precision Time Protocol. And since there are so many different ways of doing that, we sort of think of 1588 as being this catch-all that covers all these different methods, and the precise method that you choose to implement is referred to as a profile. So we have PTP, we have PTP v2, you have GPTP, and these are all called out in the various standards of IEEE. The current one right now, I think, is 1588-2008, but 1588-2020 is about to be released. But there's also IEEE 802.1 AS. And what AS does is it specifies the 1588 profile that we used for time-sensitive networking. So what we get is we get a grandmaster clock. We have an algorithm that automatically elects the best master clock of all of our endpoints and all of our devices. There's a mechanism there within the best master clock algorithm that allows, if you're doing network design and you've got a large complex system, you can actually put weighting factors in so that depending upon your particular application, you can define who's going to be elected best master clock. But you don't have to do that. The system with its defaults and its conventions will automatically take care of figuring out who the best master clock is and make that the grand master. So even though we can manually select it, typically for those of us who are audio professionals and just want to plug this network stuff together and have it work, it will behave correctly. And what this does is it provides a time reference for the entire network. We refer to this as the time of day reference, just because this is the clock reference that every one of our listeners is going to use to know when that audio packet actually has to be pushed out of the device so that we wind up in sync. So this is how we get from our original concept of Ethernet, where it's absolutely positively get that packet to the end, even if you have to send it 3 or 4 times or through different routes, to something where the packet absolutely positively gets to the end, but it's also delivered at the same time. And the accuracy that we can achieve with 802.1 AS, and for some of you on this call, you may have heard the phrase, oh, my port's reading not AS capable. That's what we're talking about. We're not saying as capable, we're saying AS capable, and that's because it's part of the IEEE 802.1 AS standard. So we can get a 1 microsecond accuracy on this delivery. Some people have observed that most of the time you might not really need that much accuracy on the delivery. So why are we bothering with this at this point in the 21st century? Well, if you look at the long history of audio, we have quite a few times where people have decided, oh, this is perfect. There's no need to worry about anything beyond that. The very first loudspeaker systems that were used in the 20s as talking pictures came in had frequency and phase response and SPL levels that to these days, I think there are probably some cell phones that are louder and more accurate. But at the time, they were thought to be more than sufficient. we are designing systems as manufacturers that need to survive more than 6 months. People don't impulse buy a big professional sound system, and they don't expect to have to replace it every year when the shiny new thing comes out. We have users that are running our products that have been in service in the field and operational for much longer than 10 years. There are some digital products shows that are running with earlier systems that we've built that are still operational, having been installed in 1999. So trying to figure out what we might need in the future was an important consideration before we started down this path. So we wanted to make sure that we weren't going to get into a position where, gee, if we just had a little bit better performance, we'd be able to do this next bold step. So let's take a look at what happens on getting our 802.1 AS communication going. It starts with our Grandmaster sending out a little message that says, hey, it's currently 12 noon at my time. And the listener receives that and says, oh, okay, I'll take a note that the Grandmaster thinks it's noon, and I will send back a reply that says, hi, I got your message that it was noon, and I received that at 12:02, so I've adjusted my clock accordingly, and here's the time I think it is, which is 12:02, and the Grandmaster gets that message, and it looks at its local time and divides the difference by 2 because the message had to go to the listener and come back, and creates an offset and sends that back out. And this negotiation is happening continuously. So we're constantly making sure that everybody is synchronized. Now, we say it's happening constantly. It's sparse enough that it doesn't consume a lot of traffic bandwidth on the network, but it's happening often enough that we can be assured that we can attain that 0.1 microsecond accuracy on the clocks between all the devices. So 1588 has a couple of styles of, as I mentioned before, of synchronization. And this method of one of the methods is end-to-end, but the method that we're actually using is peer-to-peer. And so this time exchange happens to the closest connected PTP device, which is going to be your next hop over, because your switch is also a PTP device in AVB TSN. And our Grandmaster is going to be either an endpoint, talker, listener, or it's going to be the switch. If you're a modest setup and you're an audio professional just plugging it together, it's going to be taken care of automatically. If you are a more sophisticated network engineer and you're designing and doing the network engineering for a much, much bigger system, because you can put these weightings in, you can decide from your network topology, I really want to force this particular device to be the Grandmaster because of either physical risk to certain points in the net. Maybe it's on a moving trolley and what could go wrong there, or it's on part of the building that may be powered down or whatever. So as a network engineer, you're not constrained to take the default settings. But if you're an audio professional and you've got it up and working, you don't have to get the terminal window out and go in and dial things around. So the advantages that we have is the network actually participates in the sync exchange. And by doing our peer-to-peer, the sync time is much faster. The overall network traffic, because it's just going between each point and not propagating further, it means those conversations to keep things in sync are constrained to a much smaller area for each one of the messages. So overall, our network traffic goes down. And if we connect some additional device in there that has way too much latency, it's just automatically rejected. The controller won't try to route down that path. Now, it is important to note that because the network's participating, you have to have switches that support peer-to-peer exchange. But anything that's an AVB switch provides this. That's part of being an AVB switch. So if we take a look at how this happens on a much bigger network, we start with a device here that is negotiating time, and as soon as it has its little exchanges back and forth and initially gets in sync, the message starts propagating to devices that have other connections, and they start propagating down the network until pretty soon we have the entire network staying in sync. So in this case, we've got our grandmaster at the edge of the network, but we could define it as being a central point if we needed to in our network engineering. And it all, the negotiations propagate through and set up our grandmaster for the network. And this happens automatically without user interface. So enough with the sync already. Let's move on and talk about discovery and control. So this is important. If I've got an AVB device and I plug it into the network, how does it know who it needs to talk to if it's a talker, or who it needs to listen to if it's a listener? Or if it's some other device that's neither a talker or a listener, how does it know who's out there and what it should be doing? So we have discovery and control here. So the enumeration part, you know, hi, who's out there? What can you do? We've got media control, which is I'm sending an audio stream and I'll start playing at this point in time. Please set the volume to, you know, a given variety, or hey, device X, please mute, or device A. You can tell I'm not reading that text. And this is all within the device control protocol. So if I build a box and I don't want to have a third-party controller ever be able to mute me, I don't have to advertise that mute parameter. So when the box is discovered by the third-party controller and it enumerates, it won't see mute as being something that's allowed to be adjusted. It's really important to make sure that we've got a common protocol to connect for all of the devices. So it doesn't do us any good if we don't agree upon the language that's going to be used to exchange these commands back and forth. So there are all sorts of commands that are out there right now. Currently, Avnu and Milan are using AVDEC, which is the IEEE 1722.1 standard. And it provides quite a broad palette of things that can be controlled in that, as well as mechanisms for discovering things that it doesn't know about and getting information from that device as to what that control is and how it should be managed. There are some other protocols that I'm sure you've seen go by and have heard of. I'm not going to go into those because I think I'm behind in my original schedule. So how are the AVB connections made? I'll just pop up some examples here of some AVB controllers on the screen. This is one made by Audio Science, part of their Hono line. This is their AVB controller. I'm sure this looks very familiar to anybody who's dealt with a patch bay. This is just, we've got talkers that are on the rows and listeners are on the columns, and so we put a cross point in. There is an open source project that's out there called Hive, and Hive provides a very nice, very sophisticated controller. This is just one view of many that you can have. Again, it uses a similar model of a matrix there with talkers on the rows and listeners on the columns. But you can also, if you are a system tech or you need to dive in further, you can click on one of the talkers in the list and you get details in the right pane, and you can actually dive in as deep as you want to go to find out details of what's going on under the hood in that connection. So when you're troubleshooting things on the network, this can be quite useful. Again, this is open source and it's freeware. I invite everybody to go ahead and download Hive and play with it. For those of us who are more traditional in sets, there are people that are working on graphic connections between things. So here is a screenshot of the controller that I'm using here in my studio, connecting between various Macintoshes and some other devices that some of you will recognize the model numbers of. And in order to make a connection, it's very graphical. I click on a device and I drag over to where I want that signal to route, and I get a little table that asks me which one of the audio channels I want to connect, and I just tick off the boxes and it's done. So personally, I find a graphic schematic-like representation closer to the way I think, as opposed to a big matrix. But there are other people that a big Excel-like matrix are quite natural to them. So within Milan, we have the definition for what the controller does under the hood, and the user interface side of it is up to you to find the controller that you want to use and then use it with Milan devices to make those connections. So moving on, let's talk about reliability. How can we make sure that our media packets actually arrive on time? Well, let's take a moment and think about why is this important? You know, we've talked about the advantages that we have of moving media over a network. We've got scalability, adding more channels, adding more devices. Is relatively inexpensive compared to running big multi-channel snakes or running additional tie lines or things like that. Distance, we don't have the problem in distance that we do with an analog line. If I'm trying to run an analog signal all the way around the park to provide background music, and that run is 5 kilometers, I'm going to have to do some things in order to make sure that the fidelity at the far end of that analog signal has not been grossly compromised. But by using a digital transport, it's great because the digital data at the start and the digital data at the end are going to be exactly the same. So I don't have any media loss over the transport. I know there's some hardcore network types that are in on the call here. So there are, of course, nothing in the universe is perfect, but for the most part, this is true. And as an audio professional, I don't have to worry about some of the tiny details. This just happens nicely for me. We've got the advantage, once everything is up on the network, of completely reconfiguring our routing remotely on the fly. So I can send commands out using my controller to all my talkers and listeners and have them connect to different streams. So if I need to repatch or change around, I no longer have to send somebody to a patch bay in a remote room. I can actually do it over the network. Because the system automatically takes care of the bandwidth allocation, I don't have to worry about losing packets. I don't have to worry about collisions and the rest. The network and the intelligence built into the network are taking care of that and giving my media packets priority. So the mechanism that's used to do this is, once again, another IEEE standard. In this case, it's 802.1 QAT. And this handles what's known as the Stream Reservation Protocol, SRP. So basically, our talker advertises a stream on the network. Hey, I've got this stream. If anybody would like it, here I am, and I have it available. And a listener receives that announced message and says, oh, I would like to listen to that. And so it decides to connect to that. And as part of the connection mechanism, the path all the way from the listener back to the talker is checked, and each one of the switches is queried. And do you have enough bandwidth for this? Is there going to be space on your network link in order to move this data? This is how much space I'm going to need. And once everybody along the path has checked in and said, yes, we're good to go, then that stream is started up. And that bandwidth is held in reserve. It can't be used by anybody else. And this is a process that's unique to AVB, and it doesn't require any user intervention. You use your controller and say, I want to connect to this talker. And if you see the talker in the list, it's because there should be bandwidth available. And before it makes the connection and gives you the little green dot or the green line that says, yes, everything's connected, it's gone out and made the necessary reservations and made the connections. And this all happens in the blink of an eye. So that's how the connection is made. Graphically, if we want to look at that, we've got the talker advertise goes out, hey, I've got this. The listener comes back and says, hey, I'm ready to listen to this. And it goes back to our talker, and then the media starts flowing. And so we get our signal arriving in a timely fashion. And this is all thanks to the Stream Reservation Protocol. We've also got another IEEE protocol at work here. Of course we do. It's 802.1 QAT. And what this does is this allows us to reserve part of the bandwidth for our time-sensitive packets while leaving the other network traffic alone. And you can see the graphic artist who put this slide together for me obviously thought that other network traffic deserved more bandwidth than our time-sensitive traffic. But being an audio professional, I tend to perhaps put my priorities in another direction. But so what's happening on bandwidth reservation? And again, this is a parameter that's user definable. By default, we're using 75% of the network to hold a reservation. But if you needed to dial that up or down, you could do that. And if you tried to make a connection where it exceeded the available bandwidth, your controller is going to come back and give you a little message that says, nope, this isn't going to make it. And depending upon the controller and the talker and what they support, they may offer to crank the video down a bit in bit rate, which, you know, being an audio professional, that would be my first choice, is let's compromise the video. Part of the mechanism that's setting this up is the network automatically sets up a VLAN that's being used by our time-sensitive data that's moving stuff around. on that. So this is all taken care of automatically by AVB TSN. So if you've got AVB switches, which of course you will have because you need bandwidth reservation and you need our clocking data, AVB TSN automatically sets up the VLAN that's needed for that. So once again, our desire as manufacturers is to make sure that our end users are able to concentrate on what's important to them, which in the case of an audio professional is just getting the right mix of the audio delivered to the ears with high fidelity and not spending a bunch of time at a terminal window typing in cryptic commands and the rest. So this is one of the things that happens automatically under the hood. The VLANs are set up to allow AVB devices to communicate with other AVB devices, and keeping the legacy traffic, the non-AVB traffic, isolated from that, and keeping our reserve bandwidth up on the VLAN. We the term that you may have heard for this that covers this particular part of what's going on is MVRP, Multiple VLAN Reservation Protocol. And VLAN, of course, is the Virtual Local Area Network. So here we have nested acronyms. We also have, we want to manage our forwarding and the queuing of what's going on these audio on the audio traffic that's going out. So if we've got AVB on a switch and we've turned that on, some switches flip it on automatically. Some still require you to issue a command when you first buy the switch, and once you've set that, it stays on forever. But you've got priority queuing, which are AVB TSN traffic needs. It should have the priority. Then there's also this parameter called traffic shaping. So how do we deal with making sure that the right traffic has the right priority and gets through? You know, this is managing our packets. So we use traffic shaping, and there are a couple of ways that one could do traffic shaping. In the case of AVB TSN Milan, this is happening at each switch point on the network. So here's a little graph here that talks about a couple of different ways that Ethernet deals with a lot of traffic on the network. One is pruning, where we just saw off the extra traffic. It gets discarded, and that's okay because a message will come back to the talker that says, hey, I didn't get character number 27 on this device that I'm trying to output to the printer. Would you please resend that? And it gets resent where there winds up being some space. So that the top graph there from left to right shows you what's happening with pruning. We're just sawing things off. This does not work for time-sensitive media. We wind up with holes in our audio and holes in our video. Not good at all. So instead, what we actually want to do is we want to do traffic shaping. And what this does is when we've got a big burst of traffic from the device, this feeds into buffers so that it can all go out sequentially. And so the result is, instead of these holes in the traffic where we slice stuff out, we actually get a constant flow. Another way of looking at it is if we were to take a look at the traffic coming out, and each bar is just a little packet of data that's going out over time. So we've got a big burst that's happening there in the middle, and then we've got some blank spaces where nothing was happening at that particular point in time. With traffic shaping and our buffers and the rest, we can actually even that out. So now every single packet that we want to transmit, because it's got our priority setup on it, actually makes it out, and we've got very even traffic. So another way of looking at this is graphically, of course, and the little colored dots are basically your different message types that are going on there. And you can see that we've got different levels of queues, including the AVB TSN queue. Now, if you notice, our low priority queue there just dumped some packets because there wasn't space in the queue for it. Actually, all of the queues do that, but we ran out of time in doing the animation in order to do that clever animation for all of these. So instead, I just have the low priority queue showing that dropped packets. But you notice our AVB TSN queue up there actually buffers up, and then at regular points in time, every 0.125 microseconds, we send out a burst of the AVB TSN data. So this is our traffic shapes data to make sure that it actually goes out with an even flow, and that we're properly managing our traffic, and everybody else being legacy traffic or non-real-time priority traffic will wind up having to do the resend. So this is a normal part of Ethernet, and this is how we ensure that our latency requirements are upheld and that we have deterministic delivery of our audio and video packets across the network. So transport, how does this media actually get across the network? So we've got media data that's audio or video, and each one of our packets has a sequence ID saying I'm, packet number 1, packet number 2. They're sequential in order, so our listener can tell was something dropped. And there's also the timing and synchronization information, that timestamp that's on the packet that says, at this point in time, this is when you need to push that audio packet out the port on your device, whether it's audio or video. And so everybody on the network outputs the same sample at the same time. So we've got our master clock here distributing it. Once again, I'm starting to sound like a stuck buffer, I'm sure, but the transport needs to be time aware for this time aware system to work. So we've got our media packet stamped with a playback time. We call this the presentation time. So again, with the animated graphics, I timestamp that it's now 2 milliseconds. So I send my data out. The first hop, the endpoints now already have the data. At the other endpoints, there's 1 hop delay in between the two, but when they output the audio, it all happens at the same time because they're looking at that, that timestamp. I should mention that AVB AVB TSN is actually transport agnostic. We happen to be moving it over Ethernet right now. It uses the IEEE standard 1722, which is a packet format that's been optimized for AV and can support a number of media types on it. So how does 1722.1 put its stuff together? Well, we need the presentation time embedded. We can embed the media clock. We do that. And if we want to do multiple media clocks in the rest, we can actually send just a time-sensitive stream, a 1722 stream around that only has media clock in it. Really, that's just the payload that's being delivered, and the delivery is time-sensitive. So let's talk about transport efficiency. So I'm sure everybody's heard of broadcast and unicast. Broadcast, of course, is actually a special case of multicast where we're sending a message to every single device on the network, where unicast is point to point. It's sending from one device to one device. So If we're doing unicasting to multiple devices, we have to send multiple copies of the same data out to each one of those receivers. If you take a look at the graphic here on stream, you can see that that first hop from our initial talker to the switch actually has 5 times more streams than any one of the hops to the final receivers. And the hop between the two switches is 3 times the amount of data. So not very efficient at all. And you're going to be limited by the bandwidth of the transmitter as to how many end devices you can reach. So if we've got high bandwidth media, whether it's 4K or 8K video or lots of audio channels, this really doesn't work very well. You're going to wind up into a situation where you need to multicast. So what do we get to do with multicasting? With multicasting, we go one message that is addressed to a multiple set of receivers. Now, if we don't have any way of identifying exactly which receivers need this multicast, it winds up becoming a broadcast, which means it goes to everybody on the path, which means there's always the possibility that if you've got somebody who isn't the intended target for that data, they might be busy with some other traffic and you might actually overload them. So this gets even worse when you've got multiple sources that are transmitting and they're trying to multicast out, and this is going out as a broadcast because there's no selectivity on it, and it gets worse. So multicasting is supposed to be more efficient media networking. What's going on here? Well, the default is multicast is the same as broadcast unless we've got some mechanism active that will allow us to direct a given multicast to specific listeners. So a switch will tend to flood multicast traffic to every port unless these mechanisms are turned on. AVB TSN Milan uses selective multicast forwarding. And to do that, we do this with the IEEE standard that is called Stream Reservation Protocol. I'm sure you've also heard of IGMP snooping. This is something that's used on IPv4 on some network protocols, and by enabling IGMP snooping, this is just a way of tagging a multicast so that it can identify which listener it needs to go to. You do have to have switches that support IGMP snooping. So while there's a tendency to refer to some protocols as needing specialized switches, really, if you go back in electronics history and look at the way things have gone, stuff initially gets rolled out in a very expensive special product. And once the utility of it's discovered, it then starts migrating into every other device, because switch manufacturers, like the rest of us building devices for people, have discovered that the more you can integrate into one device and the fewer variations that device you do, you can take advantage of economy of scale. So you can increase your bottom line as well as benefiting your customers and users. So if you've got a switch that supports IGMP snooping, which is these days almost every managed switch that's out there, you can turn that on, and this means the switch can read the label that's on the packet being transmitted that says, hey, I'm only supposed to go to these particular devices that are going to be listening to this packet. So you're not flooding the entire network. Except that the way IGMP snooping works, being a more mature network standard, you have to have an IGMP snooping querier. That's going to be one of the switches that's out there that's responsible for keeping track of the table of, hey, these are the following messages that are out there that are IGMP tagged, and this is who they need to go to. And that switch may not even have anybody connected to it that's the receiver, but it does mean that all multicast traffic has to go to that particular switch for it to build the table up to then distribute the information that manages all of this. So that can be a bottleneck in and of itself. It's problematic. With AVB TSN, we actually use the stream reservation protocol to manage all the stuff that's on the audio video transport protocol on that. So SRP is also the same mechanism that's already running, taking care of our network bandwidth and reserving that. So we already have this up and going. It means that by default we use multicast, but it's the intelligent multicast because SRP takes care of making sure that only the listeners that have requested those streams get those streams. And the switches are selective about where they forward that multicast data. So our transport efficiency now improves. So we've got one message that's going only to those listener devices out there. So this is our broadcast versus multicast again. So with our AVB TSN Milan multicasting, you can see I've got some non-receivers out there, and the switch doesn't bother to forward the multicast data to anyone who doesn't need it. And if an entire switch hop doesn't have any receivers on it, that data doesn't even have to go to that switch. So it's much more efficient use of our network. And again, this is something that happens automatically. As an audio professional, I don't have to do the network management to set this up. I don't have to tell a device that, oh, you're going to be a multicast versus a unicast. This is already known to the endpoints. This is already known to the switches. So, and of course, if we've got nobody out there that wants to hear from that talker, no traffic flows. So now we get down to the real fun part, which is interoperability. How can I make sure that if I've got two devices, they're both Milan devices, I plug them into my AVB switch, how can I make sure that they're going to work together? So what do we mean by interoperability and work together? We mean that we can actually pass audio and data between two devices and have them do something that is useful to us as an end user. So we want this end-to-end connectivity. And in order for that to happen, we've got controllers that are part of AVB TSN Milan, and these controllers might be built into the device, or they might be a third-party controller. We can actually run more than one controller at a time. So if we have several people that need to either monitor what's going on, or they're working on different devices on the same network, they need to be able to have control. So these controllers have to be able to communicate. And this is all managed by AVB TSN Milan and the IEEE standards that make this possible. So what we're heading towards is convergence in network systems. So with the AVB TSN approach, we are using the Ethernet standard in quite a variety of networks and applications. It's inherently built to traffic shape and manage all the different packet types that are going to be on the network, making sure that our time-sensitive control and time-sensitive media data actually gets through on time. It makes interoperability much easier because we now have a standard protocol that we're using for control and audio and media data. And it also means that there's information that's available from all of these AVB TSN devices into any IT management that might exist on the network. So again, if you're in a facility-wide or park-wide situation where you've got people that are taking care of the network infrastructure, because there's a lot of stuff that's going on the network besides just media, there are tools there that allow them to feel comfortable and actually look in and monitor this stuff. So how do I know if devices on the network are interoperable? Well, let's see. We could ask for people's opinions. We could use trial and error. Not really recommended on the day of the show. We could see if somebody had a list of compatible devices. You know, I could go up on the internet and look on the World Wide Web and do a Google search. And of course, we know how reliable everything is that you see up on the web can be. And nobody had ever put incorrect information up. But that really doesn't scale well because it's a volunteer effort to create those lists and keep them updated. So being part of a company that was one of the original signatories to CobraNet way back, it's been more than 20 years ago, there used to be lists of what switches worked well with CobraNet at the start, and we were all naive and hoping to make a better planet through CobraNet. But the problem was some of the switch manufacturers would keep the same model number but change the motherboard in it from value engineering standpoints, and all of a sudden it would stop working. So the lists tend to get out of date, and that doesn't work so well. We could buy all of our stuff from the same network vendor, but also discovered that it was the same network vendor that had changed their motherboards. Or there could be some kind of certification verification that vendors had to meet for interop requirements. Now, it takes a little bit longer for the ecosystem to ramp up because everybody that wants to produce a device has to go get it certified. And there has to be an agency put together that does do the certification and keeps track of that and manages all of that. And that's where the Avenue Alliance comes in. And Meyer Sound is a member of the Avenue Alliance, and there are a number of our colleague manufacturers, both of loudspeakers and other devices that are members of this. Avenue is basically a trade association. And the whole idea behind Avenue was to have this central point that could actually keep track of the kinds of housekeeping and information distribution and management of certification and test labs and the rest that none of us as audio manufacturers could deal with. The reality is that as audio manufacturers, even the biggest of us are a drop in the bucket when it comes to Ethernet devices. If you look at the number of Ethernet switches sold per minute versus the number of loudspeakers sold per day, there are orders of magnitude difference between the two. So as Meyer Sound, if we go to a switch vendor and say, hey, we'd like to buy 3,000 of this model switch, could you make it do the following? Sometimes they don't even return our phone call because 3,000 piece order versus a 250,000 piece order, which one are you going to spend traffic on? So I can't fault them for that. But by gathering together all of us who have decided that a common standard for transferring media over Ethernet would benefit all of our users and help the art as a whole move forward, we banded together. We formed a trade association, which is necessary to make sure that nobody thinks they're antitrust or collusion going on. And together, that's given us a little bit more leverage, and it's also given us the opportunity to participate in open standards like the IEEE and start not just implementing those, but driving the standards forward to incorporate more of the things that we see as important and making a difference. And the fun part of that is some of the stuff that we've identified as being necessary for pro audio, some of the manufacturing automation plants that are dealing with big steel and automotive have gone, oh, hey, you have a point there. That actually kind of makes sense. So the AVNU Alliance actually maintains certification of test labs that run the AVNU tests that ensure interoperability and standardization and make sure that everybody is complied and properly implemented the specifications together. And so to reprise from the start, what we have with Milan is this is a protocol for digital audio and video that allows for interoperability across devices. And what's important to us, first and foremost, is high fidelity. If the sound is terrible getting to the box, the sound coming out of the loudspeaker is going to be terrible. And of course, everybody's going to blame the loudspeaker, not the transport. Low latency, this is imperative for live shows. And while it's going to be a while before we have live shows, they will come back. And low latency is critical for performers. If your monitor or loudspeaker all of a sudden has the same delay as it would if acoustically you had moved it 50 feet away, this tends to have an impact to your performance. And it also has, Milan supports time-sensitive control messages. If I've got a show where I have important audio effects that have to happen, whether it's as simple as moving the sound to a given loudspeaker or changing the routing because a performer has moved to a different spot in the performance venue, I need to make sure that when I press the go button to execute that audio show control command, that it actually arrives in a timely fashion. So there is a certain amount of time sensitivity that's required for control messages. And we can also define how the redundancy can be configured. If I'm in a touring setup and I have a relatively small number of switches, I don't need that whole 2 milliseconds to go 2 switch hops. I can dial my latency down. So now I can get that monitor wedge or those in-ears even closer to the performer. As I mentioned before, all of us, when we gathered together to come up with this idea of, hey, let's take AVB, TSN and turn it into something that really makes sense for us as pro audio manufacturers and for all of our customers, because we know that our customers use not only our particular devices, but they use our colleague manufacturers' devices as well. So it's in everybody's best interest that this all work together. And it's also, for those of us making professional devices, important that we settle on a standard that will last into the future, so that we're not just taking what will work today and is acceptable today, but it also gives us some room to grow in the technology side, so that as innovations are made in our various labs and the rest, all of a sudden we're not constrained by some limit that was imposed by the transport mechanism that we chose. So that's how Milan came about. Let's see. And I just realized the next slide is out of order. So I am an example of why human beings are really bad at multitasking and trying to do two things at once. Fortunately, I don't have to listen to me while I do something else, so I can just kind of prattle at random here. But let's pop ahead again to the slides that I showed at the very top. Couple of things that we have out. You may recognize this band from down the street wherever you're at. This is an example of a tour that has been out. It's suspended at the moment, but they're running 24 of our Galaxy processors in order to distribute all of the locations in the arenas and stadiums that they're playing. There are actually 18 AVB switches involved. So there are some places, some of the destinations that are actually the full 14 hops away, the 2 milliseconds. We're also running real-time control data down the AVB TSN network from RMS. This is our telemetry from each loudspeaker reporting the performance of that loudspeaker. And we use 1722.1 on AVB to send that control data back. So we've got 197 of the loudspeakers are wired up so that the system tech from the agency that owns all those loudspeakers can keep track of them and make sure that they're all performing properly or schedule maintenance for anything that's having a problem on that. This all deploys automatically. There's not an IT professional out on the tour. It's all audio professionals that are dealing with this. And because we've got controllers built into the Galaxy modules, it's set up so that you plug it in, switch it all on, it wakes up and does its thing as it's supposed to. Let's see, where's my... Oh, I see I have. This is just some of the map plots for those of you who are used to our loudspeaker prediction program. It was just so nice and colorful, and you recognize some of the people there in the photograph that are responsible for doing the mix of the show and for making sure it all comes together. And the most interesting part to me, of course, is the smallest part of this slide here, which is actually the block diagram showing the signal path routing between some of the switches and the destinations. So that's Metallica's tour out there. Another place where AVB has been used is a sports stadium where they play the proper kind of football. This is the football that is the spherical object instead of that distorted oval shape. This one only has one Galaxy in it, but it's got 12 AVB switches, and I don't do math on Mondays, so somebody will have to add 32 and 27, but those are all the listeners that are out there around the stadium. So we're feeding our column array loudspeaker in order to provide distributed sound to everyone in the stadium. So here is another shot of, and this is the side view. If you look really close, you can see the loudspeakers on that. There's a close-up of one on the left side of the screen for you. And this is how it's all distributed and the beam angles and where they're aimed. And it's all from the central announce booth on that. So I think that's probably enough. I meant to hit that button instead. So if there are any questions that you have.
That was great, Richard. Much appreciated.
Not exactly this is how you use a Galaxy to do that, but you know, we have owner's manuals for that. And we also have a very friendly tech support department. So if you're using one of our devices and you need some details as to exactly how to get it working or update, please avail yourself. There's on the main Meyer webpage, there's a link to tech support that we have. It's very obvious to everybody but me where it's at.
Right. Well, what I find interesting and what you demonstrated very concise and very clearly is that it's a unique solution that sets it apart from alternative solutions. But the nice thing is that all of the things that you discovered ultimately are done automatically. And I think that is something really, to emphasize that it's very sophisticated, but at the same time, it's intended for audio professionals, and all of this happens automatically.
Yeah, you can have complex systems, and certainly anybody who's dealing with line arrays is dealing with a complex system. But a complex system doesn't have to be convoluted. And anytime you start talking terminal window and typing stuff in, you're into a convoluted system.
Right.
And so this is why, one of the reasons we chose to go with AVB TSN Milan.
Understood. Okay, for those that are on the that are joining us today, if you would like to ask Richard any questions, please make use of the chat. We can both see the chat, we can monitor the chat, so please pose your questions through the chat, please.
I see, could I have two AVB Milan networks, main and redundant, within the same switch on separate VLANs? Well, this gets back to the question of what do you mean by redundant? What happens if somebody trips over the power cable to that switch? Maybe you actually want to have that separate network on a separate switch for that. This is why on the Meyer devices and some others, we've chosen to put two network interface ports on there so that you could actually be redundant out to the switch level if you want. However, if you want to have some redundancy and have two different networks, yes, this is allowed. You're going to be in, depending upon what you're switching over, how are you making that redundant connection? So are we running two cables to the same switch? Are we running two of the same device? Sorry not to give you a yes/no answer because there's a little bit of complexity there in what you're asking for.
I think in the network connection guide, we refer to it as cable redundant. If you run two networks over the same switch, then the switch is not redundant, but the cabling between both ends are redundant.
The cabling between the endpoint device and the first switch is redundant, yes.
Right, right. Okay, we have a question of Clark who asks how much bandwidth is reserved for video?
Well, the default bandwidth that's available is 75% of the link. This doesn't matter whether it's a 100 megabit link or a gigabit or a 10 gig or a 40 gig link. For AVB TSN, the default is 75%. You can crank that up or crank it down. The decision as to how much the audio department is going to share with the video department is a negotiation that the audio department needs to have with the video department to decide what in the network structure is going to be necessary. Certainly, if you want to do uncompressed 8K video up to the screens, then chances are you're going to need your own 40 gigabit links to do that. And if you've got some to spare for audio, we'll use it, but that's a network engineering selection. But from the end user standpoint, again, this can be managed by your controller and the order that you decide to make the connections, because once bandwidth is reserved, it doesn't matter whether it's actually being consumed at that instant or not. It is reserved, and the stream that reserved it will have priority on
Excellent. Okay, well, other than that, it appears that the chat is cooling down from what I can tell, which means that thank you very much, Richard, for doing this awesome job of explaining us the appeal of AVB. And that means that if it's okay with you, I'm going to follow up with some household notes and make sure that we are all know where to find the recording of today's webinar, because as always, these webinars are being recorded and will be shared through our Thinking Sound YouTube channel. But before I show you that, Richard, once again, thank you very much, our digital product solution architect, for doing a wonderful job of explaining Milan AVB and its appeal. As I said, the recording of this webinar will be available on our YouTube channel called Thinking Sound. So for those that want to watch it again, be sure to go there. As for future webinars this week, on Wednesday, June 3rd, I will be doing a webinar on Compass Go. We already looked at Galaxy devices. We already looked at the Compass control software, the mature version, which runs on our computers, but there's also an iPad app, an iOS app called Compass Go, and we'll be looking at that this Wednesday at 6 p.m. Central European Time, 9 a.m. Pacific Time. And that means that without further ado, thank you very much. Thank you, Richard, once more. Thank you for being here. Please stay safe, please stay healthy, and hopefully see you this Wednesday. Bye-bye.